Okay, so the way I understood it is that there's someone named iDubbbz who used to have a content. No, I used to have a series called Content Cop,
So I've heard.
where you like go around and evaluate other content creators and you like point out how they're bad. And apparently, all of these except one, the most recent one, got deleted because of the number of slurs in them. So we're talking about that part of YouTube, right? Anyways, this person made a content cop about H3 Productions and specifically Ethan Klein. And you'll never guess what it's related to. Our favorite current event discussion, Israel Palestine. So, anyways, if you want to have why Zionism is bad explained to you by someone that professionally used racial slurs until a couple years ago, there is a 1 hour long YouTube video that you will love. And if you don't want to do that, I have given you a very cool assignment on making heaps. So I don't want to hear anything about like, oh, I was busy, right? The only two things you can do are watch YouTube and make heaps, right? Right, that's true. Yeah, I need some affirmations. Yeah, that's what I thought. Okay. Um the heap T public APIs are posted. It's only two things that are an awful lot like methods, right? So this is the either the constructor or initializer, probably. I just stack allocated mine, so this doesn't return a pointer. Um, blah blah blah. Insert. I passed this one a pointer because it has to update heap. So what does this do? Oh, you get an element, you shove it in the heap, and then what's max pop do? Returns an element to the point. Now, I implemented my heap, and I'm asking you to implement your heap size agnostic. This means you can put things of any size in it, but everything in the heap has to be the same size. Okay? Why did I do this? I wanted to force you to do some pointer arithmetic, right? We love pointer arithmetic. Remember pointer arithmetic? That's where if I add 1 to the location of an integer, it increases by 4, right? You can't do that with all this nonsense because it doesn't work. So you're actually going to have to figure out how to do that. So this is a pointer arithmetic and also Merkle tree combined assignment. It might look like an assignment you would just get in a data structures class taught in C, right? But that's not what it is. It is directly aligned with the learning objectives of this class. Trust me, right? I wouldn't lie to you. Have I ever lied to you? Okay, that's a bad example. Do I seem like I am currently lying to you? Okay, that's also a bad example. It's beneficial to you to pretend I'm not lying to you, right? That's it. That's it. Okay. Um, no, I really had every intention of assigning you a Merkle tree, and then I looked at implementing it, and I was like, this is so much less interesting than a heap. So I just assigned a heap. Um, Speaking of things that are less interesting than heaps, we got Merkle trees. Woo! Um, I've been trying to remember to call them hash trees. It hasn't really worked. I just keep calling them Merkle trees. I also don't know if I'm saying Merkle correctly. I keep thinking they're named after Angela Merkel, the former chancellor of. It's presumably not called United Germany anymore, but the one country that's both Germany's, right? That country. Um, and also Angela Merkel's like maybe retired, and now there's someone named like Olaf or something. Anyone follow European politics at all? You don't follow streamer drama. You don't follow European politics. Okay, you follow. Yes, thank you. Good for you. What is? Does Germany have a chancellor or a prime minister? Do you know? Oh my gosh, they cloned Macron. Okay, cool. Um, Europe has exactly one trick, and it's centrism sponsored by big banks. And they keep being like, "Why doesn't this work? Why doesn't this work?" It's because the banks are on fire. Okay. So today we're gonna refresh trees. Then we're gonna look at heaps. Then we're gonna look at Merkle trees. Um, Why is this in this class? Well, Merkle trees are like absolutely, completely 150% mandatory for Bitcoin. So there was absolutely no way around it. Independently, um, Merkle trees are complete or perfect trees, depending on who you ask, and I will have who we asked in the slides. And when a tree is either complete or perfect, there is a way you can store it by only storing the nodes and all of the edges being implied by how you store the nodes. And that's pretty cool. So we're going to construct a correspondence between a type of graph and a type of array. And that is used for both heaps and for Merkle trees, which was quite interesting to me. I would like you to be able to think about, at the end of this term, and hopefully we're there, I spent a certain amount of time trying to get you to think that bits are just bits and they don't actually mean anything unless we want them to. I'm hoping to get to that point with abstract data types as well. So a heap is just something that has some features and some functionalities, and it just works. But there is more than one way to implement a heap, right? There's more than one way to implement a list, and so I've been trying to drive that home. One reason to drive that home is because there is more than one way to implement blockchain, right? And so if our resultant work across the course of the semester is to implement blockchain, well, we have to have some understanding of what it means to implement a blockchain. And what it means is to have basically a piece of code that implements certain capabilities, but it doesn't necessarily matter how those capabilities are implemented, okay? Trees. You remember n-ary trees, right? A tree is a type of graph. It is a type of directed acyclic graph, so there is no way to go around in circles in the trees. A graph is a set of nodes or vertices and edges, and specifically with trees, we refer to some of the vertices as the root and some of them as leaves, right? Oftentimes there is exactly one root, and oftentimes there are multiple leaves, right? And then the edges are the connections between the nodes and other nodes. And so usually this is referred to as a parent-child relationship. And I'm assuming someone will find a better way to describe it than that someday, but that's what we're dealing with now. One of the reasons this description doesn't make sense is oftentimes the children are referred to as left and right, and we all know that all children are leftists. So that makes no sense at all, right? Okay, that was kind of funny, right? Who loves communism, right? We all do. Yes, I know, right? That's because we're children. Okay. So this is the blockchain. If you can't tell what this says, that says Genesis block, which I thought was pretty clever. Do you see how cute that is? It's the Genesis block, but split into two sets of 6 characters. Genesis block, right? That's cool. So there's a Genesis block. It feeds into the previous of a 4-part, we can call it a memory object or a struct, right? And so it has a previous, it has a time, it has transactions, and it has something that is used once. And that feeds in, and that goes on and on and on. Think of this as a linked list or a sequence. I do not usually think of these as array lists because we do add one thing to it at a time, and usually I do that with a linked list. Separately, the pointer size in here is very, very small compared to the size of the block, so it doesn't seem particularly inefficient to have pointers. Why is this probably not implemented with pointers? Most likely, and I looked at Bitcoin Core a lot and I couldn't figure out what they're doing. I'm guessing all of these blocks are stored in block writes, so you just write a fixed number of bits in binary to a file system. And I'm guessing if they're doing block writes, they're not using pointers for anything, right? So I suspect there's a transaction file for each block, and then there's one big file for the entire blockchain, but I don't know. What this means is that regardless of how Bitcoin is implemented, you are able to implement blockchain with your list T. List T is a one-ary tree. It is a tree where the root is the head element, the leaf is the tail element, and all of the individual nodes have both one parent and one child, exactly one of each. All of these things are directed because pointers are directed. This thing is acyclic because we don't allow nodes to point to any of their ancestors, because then we would have a list of infinite length, and that would be computationally expensive to compute the sum of, right? So if I ask you to sum up an infinite number of numbers, that would probably take a while, right? We can all understand that. We also looked at, for example, the Mocha 2 tree. So it may or may not be hot, may or may not be small, and may or may not be to go, and so on. I think um, binary trees are a special case of something called a B tree, kind of. Not exactly. They're kind of special cases of each other, and those are used to store SQL databases, as far as I know. I mistakenly thought I would have time to teach you about B trees this term, and exactly one person whose name rhymes with, let's see, Immy, right? Got very excited about that. Sorry, that will have to be a future term. But there's nothing. There's engineering. I shouldn't say engineering because that term's overloaded. There's, I guess there's engineering techniques that make working with B trees very interesting because you can optimize lots of things and make them very fast. And that is the interesting part of working with B trees. There is nothing in particular about having a ternary or a quaternary tree that makes it more exciting than binary search tree until you do extreme performance optimizations. We are already today doing performance optimizations over a binary tree. So in a way, we are optimizing a B tree. But we are not optimizing all B trees. We are optimizing a very special case. If you had the uncommon misfortune of taking data structures from me before I got sentenced to walk the plank, I taught you about binary search trees. Did any of you learn about binary search trees from your other well-loved and well-respected data structures professors? Cool. All right. Are you a Chung or Cordova year? Okay, Cordova. Okay. Binary search trees are great if you want to store a sorted list of integers, which is something I want to do all the time. Page tables are how operating systems organize memory. This is not an operating systems class, but we can think of it this way. I have informed you, and you all trust me, that executables have a stack and a heap and some memory space they work with, right? Well, that memory space exists in some broader context, and that broader context could include memory spaces for different executables that are running at the same time. For example, I can have a memory space for my terminal command prompt, and I may have a different memory space for it if it begins working in WSL. And all of that is separate from my browser here, which is existing in some other memory space. All of these memory spaces are maintained by the operating system, and some of them have interactions with each other because I can copy paste things from my browser directly into a Linux command line, right? That's a bit goofy. So somehow the operating system has to store where all of these various values are, and usually it does so in a nested data structure where there's different pages of memory, and oftentimes there are more pages of memory than can fit in a single data structure, so it became a recursive data structure at some point in history. Page tables are pretty cool. I would love to teach you about them someday. My intention is we will probably see page tables in the second semester of the systems sequence next year if you're around for that. Will we see B trees in that? I don't think we'll do B trees in the next 2 years. Okay, our use case is heavily motivated by the Bitcoin use case or the blockchain use case. I'm not really in the business of differentiating Bitcoin and blockchain. The same paper that introduced Bitcoin introduced blockchain, and I don't think there's like a strong reason to differentiate them. So I really view Bitcoin and blockchain as the same algorithm. I understand there are non-Bitcoin blockchains now, but there are certainly no non-blockchain Bitcoins, right? In our case, the thing we're going to store for the Merkle tree for the Bitcoin use case is we're going to store hash digests. We're going to store hash digests in all of our non-leaf nodes. And those hash digests are going to be the hash of each of their two children, because we're going to use a two-ary tree, or a binary tree, or a binary tree, perhaps. Whenever you, like, put something in the trash bin, do you imagine you're casting it into the binary number system? I think about this often. Okay. Like, oh no, I put it in the bin. Now it can only be expressed in bits, right? But of course, everything can only be expressed in bits. Okay, so this is totally unrelated. Okay, hear me out. What if there's only one electron, right? Because the electron can go forwards and backwards through time. And that's why all electrons appear identical, right? Right, this makes sense, right? Okay, and then what if it's even better, right? What if when it's going forward through time, it's negatively charged, and when it's going backwards through time, it's positively charged? So actually, all of the charges in the universe are from one electron going in different directions, right? This also makes perfect sense. Yeah. So, anyways, I my partner who's a chemist, I love when she comes home from work to tell her I only have one electron in my body. That's what we do for fun. Okay. I don't know why I brought that up. Oh, right, because the electron can store bit values, right? So you can actually only store one bit in the universe unless you have nonlinear time, right? This makes sense. Okay. This is why they don't let me teach physics, in case any of you are wondering. There might be other reasons, but I think that one independently is good enough. Um, Transaction review. A Bitcoin transaction and a Bitcoin chain are identical. A Bitcoin transaction is a chain of ownership. It is a digitally signed chain of ownership. Do you all remember digital signage? Okay, I'm going to say it out loud to you because I don't believe any of you actually remember it, okay? Sorry. Okay. Do you want to say it? Yeah? That is part of it. Okay. Okay, I have a transaction. The transaction contains my public key, the public key of the person I'm transacting to whom I am transacting, for whom the transact tolls, right? Okay. And it also contains an amount, okay? I take that, and that's a bunch of bits, because we love bits, don't we? They're delicious, right? There's only one of them, but it's going forward and backwards through time, so we can use it more than once. I take those bits, and I do two different things to them. I SHA-256 hash them, and I also RSA encrypt them with my private key. Then I release my public key, and also the ciphertext, and also the hash digest. So I release three things. Someone comes along and wants to see if the transaction is valid, and so what do? They take my public key and use it to decrypt the ciphertext, and they're not sure they trust me, so then they hash the decrypted ciphertext and see that they get the same hash as the hash I released. And if all of those things agree, then it's a valid transaction. If I had the coins to begin with, which is a separate question, okay? So, a transaction contains a sender, a receiver, and an amount. I usually refer to these as persons, and I should not do that. A sender receiver is not a person, right? A sender and receiver is a public key. People can have public keys, but so can other things. So for example, I could probably trick my cat into buying a Bitcoin, right? Because I could take my little kitty's little kitty paws and mash the little buttons on my computer necessary to generate a public key, right? And then that would be my cat's public key, right? Now, as my cat's legal guardian and fiduciary advisor, I would still be responsible for maintaining that Bitcoin, right? What would be my cat's Bitcoin? So my cat would have something a lot like this. And I actually reached out to my cat for comment on this, and she's not speaking yet, but she's going to open up pretty soon. So she didn't say anything about this, okay? I wasn't sure the best way to handle various nonsenses going on here, but I tried to write this relatively neutral to how key sizes are being stored, right? You don't want to implement your algorithms in such a way that the key sizes can't get bigger, because computers keep getting faster, which means key sizes should get a little bit bigger every year. Now, they don't usually get a little bit bigger every year. Usually they get bigger in chunks, where you like double their size every couple years, right? And the other thing that might double in size every couple years is how big an integer is. Now, Bitcoin's been around since 2008, and how many bits were there in the universe in 2008? Exactly one, right? Because it's going forward and backwards through time, right? Come on, that was an easy one. I gave you that. There's always only one bit. Okay, there's one electron, there's one bit. There's one, there's one neutron, but sometimes you take one of the electrons going backwards through time and attach it to it and turn it into a proton, right? Anyone love particle physics? No? Okay. Oh, yeah. Some faint nodding. Does it sound like I understand particle physics? Yeah, Sam was just like standing out there. I was gonna try and trick him into coming to class today, but I don't know. Okay, what were we doing? Right. Okay. Um. I think there's going to be 21 million Bitcoins that are divisible into some large number. Anyways, I multiplied how many Satoshis were in a Bitcoin by how many Bitcoins there's going to be, and I got 2.1 quadrillion, which is apparently around 2 to the 50th. That's more than a uint32 and smaller than a uint64, so I hard-coded this as 64 bits. And then all of the key size stuff I left as not magic numbers, right? Magic numbers are an anti-pattern, so these are all defines and type defs, okay? So I have an int buffer of key size, and I have a send. And I called these n because I only need the modulus. Everyone's using 65537 as their public key, so you actually only need the modulus, right? And if you do need to stave the public key, then it's just not that much more information. Now, one of the problems with this is I have a 4096-bit key. I have a 4096-bit modulus, and I'm trying to store things, or I'm trying to encrypt things that are bigger than the size of my modulus, and I can't do that because I'm taking values modulo other values, so I'm losing information. And so what this here says is that 64 plus 64 plus 1 is bigger than 64, which I think we all probably agreed on, right? Now, using an advanced technique that I have taught you very specifically in this class called division, I can solve this problem. 64 plus 64 plus 1 is a multiple of 3. In fact, 129 divisible by 3 is equal to 43, and 43 is less than 64. So, the way I can solve this problem is I can take 43 word blocks, I can encode them 3 times, and then I can decode them sequentially and get back the original information, right? Easy peasy. So this is the same thing here, right? We've got our digest, right? But we're going to take 3 chunks, we're going to encode the 3 chunks in up to key size, and we are also going to store our public key. So using this public key, I can take my big RSA, I can decode each of these 3 chunks, I can smoosh them back together, because I'm going to get 64 bits out of these, or 64 bytes out of these, but only 43 of them are going to be non-zero. So I'll take the 43 word blocks, put them together, I will hash them, and I will verify that the hash is the same, right? This is how I can create a signed key structure. That was really exciting. I didn't hear lots of cheers, and yeah, okay, sorry. Now it seems like I'm fishing, right? So I guess there's no way I can win. So we make a transaction struct. You probably cast it to a uint64, encrypt the chunks and hash. And I am thinking you probably do this in thirds, and then you prefix it with your public key. Why do you put the public key first? Well, someone's going to be looking for the transaction scene if you have a certain number of Bitcoins. So it makes sense to make this whole thing searchable by your public key. For example, if there was an earlier lecture this term that introduced the notion of hash tables, which there was, don't pretend I didn't teach you hash tables this term. Remember, I talked about it when I introduced SHA 256. The first 45 minutes of that class was on hash tables, right? So you know how to do key value storage. So you should probably be thinking of this as a key value pair that you can store. It represents the public ledger of who currently has Bitcoins, right? Okay, I think we all agree on that. I'm getting no signs of disagreement. How many of you are in here? You have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How is SSRD? Cool. Why did you shake your head no and give thumbs up?
I instinctually said it. I thought about it, yeah.
I'm proud of all of you. Like you giving SSRD presentations, I would also like to have confidence in my transactions, right? Am I recording this? Yes? Okay. That's a false dichotomy.
The button says stop streaming and start.
Yeah, which is a false dichotomy. Just because a button says it doesn't mean it's true.
I'm so sorry.
You're welcome for me correcting you. Okay. Okay, so we want to have confidence in these transactions. We need to know someone's not mucking about with our transactions and doing things like saying we gave all of our money to Santa Claus or the Tooth Fairy. Or Rocco's Basilisk, right? That's a common Right? Yeah, everyone, real ones know. Okay. So what do we do with our transactions? Well, of course, we hash them as one would Browns, right? And then we're going to save the hashes. But here's the problem, right? We don't have a fixed size of our transaction array, right? So we have to somehow have arbitrary sized transaction hashing. And we can't really store the hash of every single transaction in one Bitcoin block because remember, we have to SHA-256 hash those things and also compute the nonce for each of them, right? So we're going to use a little trick I like to call data structures. Bum, bum, bum. Oh, it was data structures the whole time. Everything is actually data structures. I'm sorry. I'm a data structure appreciator. When I first got here in my first term, there was more people in the data structures class that were data science majors than CS majors because it had data in the name. I don't know that we've solved that problem yet. I think now we just are like aggressively performatively mean to the data scientists. They don't take. Okay. Anyways, I love and respect every data scientist. Um, okay, so this is a hash tree. Also called a Merkle tree, also called a hash tree, right? I don't know that there's a preferred name. I've only ever heard the root of a hash tree referred to as a Merkle root, and for this reason, I cannot but help refer to all of the hash trees as Merkle trees, right? It is not contractually obligated that they contain specifically an SHA digest, but they contain some compression cryptographic hash, right? So we have a root that is the hash of two hashes. Each one of these hashes is the hash of two hashes. And this continues on down until you get to your leaves. The leaves are not just hashes. The leaves are some kind of data structures or data entry or data element or something, right? So in my case, these are transactions numbered 0 through 3. So I hash each of the transactions, and then I hash each pair of hashes, and I hash my pairs of hashes until I run out of pairs and I have a single Merkle root. And then I store that Merkle root inside my blockchain, and it is very, very difficult to alter this transaction because it poisons this hash and this hash and this hash, and therefore the blockchain hash. So these things are tamper resistant, okay? So in practice, I don't think we necessarily perceive these things as all being pointers, and we don't have to think of them as pointers. I'm going to step through a way to not think of them as pointers. We can place the transactions in a linear data structure like a stack or array list, okay? I can hash each transaction from there and store the results of all of the hashes. Now, if I'm hashing a linear data structure, I'm essentially creating a bijection to another linear data structure, right? So I can store all of those hashes in a linear data structure as well, okay? Then for each pair of hashes, I can compute the hash of the concatenation. So I take two adjacent hashes, I smoosh them together, and I compute the hash of that. It's a compression hash, so I only get 256 bits back, even though I put in 512 bits. And then I can store that somewhere. Well, I'm currently in a linear data structure, so I can store that in the next available position in my linear data structure, right? And I can just know that whatever the last position in the linear data structure is the Merkle root. And I can also do this in reverse order, right? And I'm going to repeat this until there is a single hash, the Merkle root, named after Olaf Schultz. Okay. I'm going to add two new tree terms to our definition. I have talked about leaves today. I've talked about roots. I don't think I've talked about depth, but I'm going to refer to the rightmost leaf in the last layer at some point. So let me show you a little thing that I thought was cool. This is the definition of a complete tree. This is from NIST, the National Institutes of Standards and Technologies. To my mind, this is the entity that is also responsible for ISO-C, which is C90, which is the standard that came right after C89. Maybe they're responsible for ANSI-C. They're Americans. They're not an international group, right? So they're slightly earlier to most things that are developed in the United States. Okay. So what is a complete tree? It is a tree in which every level, do we know what levels of trees are? No, I didn't introduce that, but it's not that complicated, right? It's everything that shares the same height or depth, depending on which way you're perceiving of it. Every level, except possibly the deepest, is entirely filled. What is an example of one such structure? Ah! This one! This is a satisfying such tree. Okay. I'm gonna leave that open because I might need it. Okay. Okay, at depth n, the height of the tree, all nodes are as far left as possible. So if I don't fill my last layer, I keep everything as left as possible, which means the rightmost leaf of the last layer is sort of the last transaction, right? This is a type of tree, and I think this is the fun thing here. Here's a citation to CLR 90, which is the first edition of the textbook I refer to as CLRS because I learned it on the second edition when they added S. CL and R are computer scientists. S is an industrial engineer, actually. So they added a bunch of industrial engineering algorithms. And this is the, like most famous, in my view, algorithms textbook in the world. Okay, but we can also refer to this in at least one other way. Let's see, what are these? Oh, these are examples. Okay. I want to show one other thing. Is it in the slides? I thought it was. Yes, here it is. Okay. We have complete and perfect. Sorry, I don't know what I was looking at. Perfect is a separate and related definition. Let's just look at perfect real quick. There's a link to, where is it? Perfect K-ary tree, right? Okay. This is just a K-ary tree where all leaf nodes are at the same depth, okay? So this doesn't allow for the partial final layer, in my view, which seems fine. Go back. But yeah, I'm referring to this as complete rather than perfect because CLR refers to it as complete, and I'm taking CLR as ground truth. There's no real reason to assume that whatever this is wrong. Also, this stuff was updated in 2020, which is pretty recent. I found some actually pretty recent data structures results while I was going through this class this term, which was pretty interesting. There's something called what is it? Yeah, the Fibonacci, was it a Fibonacci tree? Heap?
I think it was
And then there's a more performant version of this.
the strict Fibonacci.
Yeah, strict, is that right?
It's yeah, it was invented in 2012.
Yeah, but there's a problem with it.
Yeah.
With an update. Yeah, so here is a yeah, this is a 2025. Let's see, this is ACM. We allow them. Okay. This is a January 6, 2025, as in the reason this wasn't in the slides or plan for this lecture was because I was like halfway through prepping this course when this result came out. Right. Here's like an ultra high theoretical performance heap implementation. I guess these are absolutely atrocious in practice. But I was thinking I was going to mind control one of you into implementing one of these as a Python library this summer so I could publish the result. So anyways, if you're interested in that. Wait, what, worst case? Yeah, worst case
I
constant.
think that
No, these ones weren't. Strict wasn't amortized.
the strict was not amortized.
No, I didn't think so. And look at this. I don't, it's strict. Read the paper. It's open access. Okay. You read this paper?
Parts of it, yeah.
Oh, parts of it. Okay, so the truth comes out. Okay, wait, no, like. Okay, we're amortizing.
Like data structures.
No, this is not about. The amortization is in related work. Sorry.
In data structure research, what is currently being developed?
Apparently this. I thought it was a closed research area, and then this paper came out.
What's an open research area? I should probably just look it up actually.
Yeah, I have no idea. So I would probably like look up these people and see what they're doing. Because presumably they're doing data structures research. What I think of as the active research area for data structures is not actually that. The most impressive application of data structures I've ever seen is the Hadoop distributed file system. This was put together by ASF to make their version of the open source cloud compute clusters. And so this is like hyper optimized, extremely powerful key value storage. Anyways, to my knowledge, every single data structure that there's a reason to use is being used inside of Hadoop. Now, Hadoop is kind of losing steam over time because it's being replaced by Spark, which runs on top of Hadoop. And Spark now has a Rust kernel, which came out again, like while I was prepping this lecture, well, not this lecture, but while I was designing this course, right? So I'm assuming if I were to think of what I perceive to be data structures research, which is actually designing data structures to solve problems that have never been solved before, in some sort of language that is interesting to do that, I would perceive the open source Rust Spark kernel being the current area of active research here. And that is completely different from the theoretical proof-driven research from that Princeton team that implemented the strict Fibonacci heap, right? So those are, I think, two different ways to view it. Do you want to be designing and using data structures in an applied context, which is interesting because then you have to realize what portions of the theoretical components do and don't apply? Or do you want to consider it in a purely theoretical context and push the theoretical bounds lower? Separately, there are people that are doing a lot of complexity work, and I'm guessing they're running into data structures all the time, but I don't know what the current complexity results are. I'm guessing they're coming out of graph theory, but I don't know. Let's look at some complete trees. This is a complete tree. Why is this a complete tree? All leaves have the same height and depth. Okay, yeah. Well, all leaves always have the same height. They have the same depth here. Okay, this is also a complete tree. Why is this a complete tree? Very good. Yes. Yes, Sure, yeah. Whatever you said sounded correct. Do you want to say it again?
On the bottom layer, everything to the left is middle, and everything above it is purple.
Okay. How about this one? Is this one a complete tree? It's labeled complete, so it must be. Same reason. Everything on the last layer is leftmost, and then the second to last layer is full. I am taking these to be binary trees. I didn't actually tell you that, but I don't know that it matters. This one's incomplete because it's missing the left. It's just like the United States media landscape. Okay, takeaway. In a complete tree, we can always place all leaves in a linear data structure, like an array. Why is that? Well, we can say this is index 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2. Ah! Oh, it's a panic! Oh, gosh, we seg faulted. Oh, goodness sakes. Oh, that was so stressful for me. Did you all feel that? I've never seg faulted in real life before. I just tried to... Okay, yeah, you didn't feel anything. That's okay. No one makes me feel my own feelings. That's what I always say. In a complete binary two-area tree, there will always be roughly the same number of leaf and non-leaf nodes. Really? Is that true? Let's see. Ooh. Oh, there's only one. Wait, no, these are leaves. Okay. 4 leaves, 4 nodes. 3 leaves, 3 nodes. 4 leaves, 3 nodes. I wonder if something's going on with powers of 2 there. Better not think about it too much. We might have to write a proof. Okay? Who loves the American metalcore band Within Temptation? Yeah, that one's a deep cut. I don't think anyone has listened to them except me. Are they American? They're Dutch? I've never felt so betrayed. Okay. Anyways, you may be within temptation if you are a Dutch 1996 doom metal band about to rebrand into gothic metal, right? But I'm going to urge you to not be in temptation, okay? Here is one way to implement a Merkle tree. This is a way to implement a Merkle tree. I'm not going to say this is not a way to implement a Merkle tree. There is one nasty issue that is going to impact you if you do this. Okay, we take a hash tree struct. We slap a digest in it. Does the term digest make sense to you? Did you all have exposure to, like, Reader's Digest when you were children? And it was, like, the short versions of books, so you could, like, read a digest copy of it and then talk to your friends at book club. But you were, like, too busy probably playing chess or something. Okay, so a digest is a shortened version of something, right? So I have a 256-bit digest in here, and then I could have pointers to a left and right tree, right? But this does lead to one obvious problem, which is that this doesn't differentiate nodes that aren't leaves and nodes that are leaves. And the problem with that is, of course, is that the nodes that are leaves are supposed to be pointing to a transaction and not to another node. And so I was gonna teach you about tagged unions, right? And then I realized that you don't need to know about tagged unions if you use linear data structures. See, it's the problem, Jimmy, and I see you're in pain here, right? But you think those bits for those tags are free?
No.
Someone has to pay for those bits. And am I gonna pay for them? No, I don't pay for bits. I only steal bits. Okay. I'm going to present an alternative to the tagged union, which you can look up if you want to. I used to think tagged unions were interesting, and I have not seen a lot of them around, so I stopped teaching them. And also to using a binary tree structure for this. We are going to have binary trees. They are going to be binary trees, but we are not going to use pointers as edges. We're just going to intuit what the edges are. Okay, so I'm going to do this using heaps. This is cool. Heaps can be implemented by storing nodes only and determining what connections there are or what edges there are by the positions nodes have in a linear data structure, not even in a matrix. I'm not even going to put these things in a matrix. I know we all love The Matrix. It was the best movie to come out in the 90s, right? Okay, wait, no. Have you all seen The Matrix? Okay, that's good. I wonder what the oldest movie we've collectively heard of is. So you certainly heard of Jurassic Park, but that's because there's new ones coming out, right? No. Is that the first one? That sounds like it slaps.
You freaked out. Train's like coming from the big screen. I've seen the movie before in my life. That's more convincing. Movie. You know,
I should have embedded that movie in the trains lecture. Remember Graph's Trains Amtrak? Okay. Right. So here's the deal. Heaps are often called priority queues. And they're so often called priority queues. This is another thing where, like, big data structures wants you all to know the difference between abstract data types and data structures, and no one actually knows the difference. Because priority queue is an abstract data type. And it is so often used to refer to specifically the heaped implementation that now there are other abstract data types that are described as being implemented with priority queues, which doesn't make sense. So just call everything a data structure, okay? Why is it called priority, though? Well, a heap is nonlinear in the sense that, well, I mean, it's just a graph under the hood, right? And graphs aren't lines, they're different things. Now, a linked list is basically a graph that's a line, but still, there's all those pointers in there, right? And we can linearize it, but the real thing a heap does that's useful is it keeps its either minimal or maximal element at its root. And this is useful to us in the following way. You might be an operating system, and you might have a series of tasks that have different importances, or perhaps priorities. For example, you could be Windows OS implemented on AMD 64 chips. And AMD 64 chips have 4 current privilege levels, 0 through 3, because they have 2 bits that determine the current privilege level. And at any given time, if a request for operating system resources is made by something that has current privilege level 0, which is the lowest and therefore highest privilege level, and something that has current privilege level 3 is using that resource, the current privilege level 3 thing will be evicted from the resource, which is usually RAM or a processor core or something, and the current privilege 0 thing will run on those cores and then complete its task. So what that means is the operating system is scheduling tasks that run on the operating system based on the current priority of the tasks. Now, someone, the operating system, has to maintain the list of all the current outstanding tasks that have to be done. Operating systems are really just glorified to-do lists, right? So it can store its to-do list inside a heap data structure. Every time it has resources available, it just pops the root off of the heap. Whatever is at the root is always the highest priority by construction, so all it has to do is maintain the heap, and it doesn't have to scan and look for someone to give permission to start running at any given time. So that is one use case of the heap. I also use the heap to decide which one of you I respond to the emails to first. Some of you may be extremely stressed out that the advising registration window opens on April 21st, and I haven't approved your classes yet. Not to worry. I am going to drink a ton of coffee tomorrow morning and advise every single remaining student. So if you have friends that need an advisor, just throw them on the stack. Oh, throw them on the heap. And the heap is priority sorted by how many semesters you have until graduation. So unless you're 0, then you don't have rights. Okay, let's make a heap. All right. I love heaps. I'm going to look at my watch. Oh my gosh. How long have I been talking? Isn't this a fun class? Okay. You don't have to say yes. Okay. Wait, no, okay. On average, no. So, imagine the median fun class, right? Just postulate the existence of a class that is the median amount of fun of your classes. Is this class more or less fun than that class? Yeah, I think it's more. What is the median class? This is the. Yes! I'm a measure of central tendency.
Maybe.
For the record, I would like to submit that I do have feelings that can be hurt. Okay. Empty heap. The empty heap is where I keep my feelings that can be hurt. Psych, I have exactly 0 feelings that can be hurt, which doesn't mean I have no feelings that can be hurt. Okay. Heaps are usually based on binary trees. So I'm going to make a binary tree as an example. I'm going to start with an empty heap. It looks like this. See, it doesn't look like anything. Okay, let's insert an element to our heap. Oh, we're going to insert 128, our favorite power of 2 that is less than 255, right? Because it's big and it's right in the middle. So I'm going to insert 128 as an initial value. It is the maximum and it is also the root. So the first heap insert is not too complicated at all, pretty easy to work with, right? It's just an all-around good time. What am I going to do next? Well, I'm going to insert 64. And to insert a value, why are the I's in insert capitalized? That's wild. Okay. Oh, I was calling it add, and then I realized you shouldn't call it add because addition is already used. So I find replaced insert, and I didn't do a capitalization where find replace. Okay. To insert a value, we insert an unpopulated node that would make a complete tree of appropriate size. In this case, this is 128, the root, having a single child. This is the leftmost child, but I'm depicting it as directly south, right? And if I mouse over this, it is labeled finite automata. This is not a finite automata. It's just all of my digraphs are called finite automata because I always forget to change the name of the title. So in this case, in a binary tree, the first child of 128 is the next thing we'll add. Okay, I'm going to insert 64. Where's the 64 going to go? I'm going to populate the novel node with 64. I 0 prefix this just to force my graph visualization library to make the circles the same size, which I thought looked a little nicer. I note that 64 is less than 128, so the heap property of the highest value being stored in the root is maintained. Okay, so I don't have to do anything else. This is AOK, which is named after Ada, Oklahoma, which is named after Ada Lovelace, the first computer scientist. You have to put that stuff in there, okay? Don't you feel like it would be confusing if I didn't specify what AOK means? Right? That's what I thought. Okay. I also really like that Ada Lovelace described herself, I think, as like, what was it, like a poetic scientist or something? That's cool. I like the idea that we're not writing code, we're writing poetry. Because I don't really vibe with code. I think code's boo, but poetry, yay. Okay. So we're going to reduce, reuse, recycle, and we're going to insert 192 in the exact same way. I'm going to add an unpopulated node that fills out the complete tree. So this is now the right child of 128. and there's not currently a value in there, okay? We're going to slap the value in there, 192. Uh-oh, uh-oh, everyone say uh-oh. Right, that's what I thought. I knew you'd all say uh-oh. That's the heap property has been violated. The maximal value is no longer in the root. So what do we have to do? We have to do what I like to call a switcheroo. Oh no, we've done a switcheroo. Look at, see how they were switcherooed? Switcheroo is a component of the operation called heapify. I'm gonna make you write a heapify. Someone turned in this assignment already, which is kind of weird. Not someone in this room, actually. Yeah, no, one of the MSCS students did it. I was like, don't you have... Okay. There's nothing wrong with turning in assignments early. Okay. This student also turned it in before I finished setting the function types. So I don't know that the autograder will work, but that's okay. So in a loop, you do a swap-a-rooney, or a switcheroo, or a swaggity-swoogity, and you change the locations of 192 and 128. Now, it's important you do a swap, because you can't afford to lose any of these values, right? All these values cost money. You think these bits are free? No, I have to pay for these bits, right? And I don't like paying for bits, right? And if you implemented this with pointers, then there's even extra bits in here, because 192 only takes 8 bits to store, right? But if you've got 2 pointers in here, right, that's an extra 8 times 8 times 2 bits, which is 128. Okay, so you swap the new value, and you just keep doing the swap-a-rooney until you run out of things that are bigger than you, that are your children. So what this says is that parents are big mode, okay? Oh, that was a good one. No reactions, that's okay. To insert a value, what am I going to do? I'm once again going to populate the leftmost node of the last layer. Now, I filled layer, we can call this layer 0 or 1 or 2, probably. And having filled this layer, we're going to need to go to a new layer. We're going to go all the way to the left, so we're going to look at the leftmost child of 64, okay? I'm going to insert a 96 there, and then what's going to happen? Okay. I put a 96 in. Big uh-oh, right? 96 is bigger than 64, but it's also less than 192. So I do a single upward swap in heapify. Look at this. 96 is greater than or equal to 64, so I swap 96 with 64. 96 is less than or equal to 192, so I do not continue swapping. It doesn't matter if you swap when things are equal or not, because they're equal. No one cares. Now, there is such thing as stable sort, and you can learn about that in your algorithms class, okay? So, structs, right? This is a possible way to implement this. But I would argue it is bad, and I'm arguing that it is bad on this basis. This is 8 bits of information. This is 8 bytes of information, so 64 bytes, 64 bytes. That is extremely wasteful. This is a 16x waste ratio, right? Wasting large amounts of bits is bad. That's why 496T was slow, right? So what am I going to do instead? My heap is just going to be a uint 8T star. I am just going to use an array, and I'm just going to know what I'm doing, and I'm going to keep track of my thoughts. Now, I'll probably need some assisting information with this and end up putting it back inside a structure, right? But for now, I'm just going to treat this as an array. Overhead of 0, or at least constant overhead if I'm just tracking diagnostic information about it. So, what we're going to do, we're going to insert new elements into the next available position. This is the same as a stack push, or perhaps a queue push, right? This is a priority queue. So we're just going to implement this directly on top of an array. How are we going to do that? Well, this is how I imagine heaps being encoded in actual system memory, right? So even though I understand that there is an edge from 192 to 128 and an edge from 192 to 96, I do not denote those on my array. I simply put all of the entries into my array in order. I take the root, then its children, then their children, right? And there is an implied edge from things to them multiplied by 2, right? So there's an implied edge from 0 to 1, 0 to 2, and from 1 to 3, right? And so those things are roughly times 2 from each other, and we can get the precise numbers to work better. I would like some audible head rattling that you understand that I can put a heap inside an array. Okay. It's pretty weird. Okay. So we're going to step through side by side with graph view and with array view, and we're going to chuck a 160 in here. They call it the Xbox 160 because you turn 160 degrees and then walk away. Okay. It's the best I got on short notice. So we're going to create new nodes. These are leaves, but we can call them nodes as well because a leaf is a case-if node. And we're going to put them in the final or terminating position, right? Okay. Nothing in them there. Okay, then we're going to load 160 in there. Okay. Now watch how we perform heapify. 160 is going to compare itself to its parent. How does it know where its parent is? Well, it understands the positionality of the array. And so 160 knows that its parent is 96. This is a simple linear combination. We're just computing a line. And I'll show you the mathematics. The reason to not show the mathematics is you have to decide if you're 0 or 1 indexing, right? Okay. So 160 knows that its parent is 96. This is just like how baby ducklings know that the first thing they imprint upon is their parent, right? So 160 is imprinting on 96. We perform our first swap. We move the 160 and the 96. We swap them. And then we don't have to do a second swap because 160 is less than 192. Okay. Let's look at this with respect to indices. 160 is inserted as the element at 0 index location 4. So there it is. 0, 1, 2, 3, 4. 160 is at position 4. We swap it with the value at position 1. That's a little bit annoying. And you're probably realizing if you add 1 to each of these things, this becomes a 5. And this becomes a 2. And 5 int divide 2 is 2, which means you can just int divide everything. This makes a lot of sense because everything has 2 children, right? And for example, if we like increase this to 2, then if we 2 int divide it, we get 1, so we preserve that. So I'm going to recommend you at least think about, and I only thought about it, I didn't actually do it in practice. And if you think about this enough, then you stop getting off by 1 errors. I'm going to recommend 1 indexing for this data structure application. Now, there's something I think politically important here too, which is there's a lot of 0 index chauvinists running around the world, masquerading as computer scientists. The heap is one of the most fundamental, basic, and widely agreed upon data structures, and it is comically ludicrously easier to understand it if you use 1 indexing. This is a very, very strong argument for 1 indexing. Now, I gave you an extremely cursed heap implementation, but if you implement these heaps directly as void stars, so an array of void stars, then you can put the size t in the first element, because size t's and void stars are the same thing, and you can have a Pascal array heap that is incidentally 1 indexed, and that is just like super easy and nice to work with, okay? So that is really cool. Anyways, I think it is easy enough to say just 1 index it, just throw out those extra 64 bits. I'll pay for them, because it's a constant amount of bits, and I only charge you for asymptotic bits. So, how do we do that? 2 int div 2 is 1. 3 int div 2 is 1. 1 is the parent of 2 and 3. 4 int div 2 is 2. 5 int div 2 is 2. 160 is the parent of 64 and 96. So, I'm recommending a 1 index in this case. I'm also recommending thinking critically about whether you 0 or 1 index. Usually things are easier if you're 0 index, right? Sometimes they're easier if you 1 index. Okay, let's insert 224. The next index is 6. We insert the 224 there. That's probably a problem. What is 6 int div 2? What is 6 divided by 2? 3, thank you. What is 6 integer divided by 2?
3.
Also 3, right, okay. So 224 is a baby duckling and is an imprinting on 128, right? As have we all. We all love 128. 128 was my first true love of all of the powers of 2, right? Liked it way better than 64. 64 is just kind of gross, right? Not. The sum of your digits should not be 10. Sorry, what? The sum of its digits is 10. It feels... No, it feels like it should be a multiple of or power of 10 or something. It's like, no. No, I mean, the prime factorization of 6 contains 3. I don't love it, right? Like 128, that's a power of 2. Its decimal expression is 3 powers of 2 concatenated. That's cool. Okay. All right. Yeah. And if the sum of those digits is 2. Yeah. Yeah, they call me the wrong prover because I prove things that are wrong so often. Okay. Anyways, we're heapifying. I've got chills. They're heapifying. Any Grease appreciators? Yeah, okay. All right, so we do a swap-a-rooney. Look at that. See the swap? See the 224 and 128. I spent so long making these graphics, by the way, and I did not make them for you. I made them for me. This is just for me. You're allowed to watch them. Okay. And then what do we do? Oh, 224 has been born again anew. I always often think of this as waking up in the Hunter's Dream in Bloodborne. That's what I imagine, right? And it once again imprints like a baby duckling onto 192. 192, great number, all around great number. Why is it a great number? Well, the sum of its digits is 12, and the sum of those digits is 3, and the sum of those digits is also 3. So that's just cool, right? Okay. Well, the sum of yeah. Okay, never mind. Moving on. Okay, so it is cool that the sum of the digits of 12 is 3, and 12 is also divisible by 3, right? Isn't that cool? I think like 12 is this like graceful, elegant number. I think for that reason, right? And I think that's probably why it's divisible. Yeah, that's because 3 is base. Okay. Wait, no, hold on. Okay, so 27 is a multiple of 3, and the sum of 27's digits is 9, which is a multiple of 3, but it's not 3 itself. And it's which power of 3? Oh, is that why? I think this would be a lot easier if we only used binary. Does everyone know what's happening on this slide? Correct. Look. Look, 224 was the largest of the integers. And so it is now in the lowest numbered index. Okay? So it's heapified. And then you can say, oh, look, oh, it looks just like the graph representation, right? And I threw in indices here in the graph representation for you all. Well, that's not true. I did it for me. Heaps. Did y'all have heaps of fun?
Yeah.
Okay. I'm so hungry. Anyone else hungry? Can I hear it for being hungry? Who loves blood sugar? That's just two good things, right? Okay. Create a Merkle tree. All non-leaf nodes are hashes, and all leaf nodes are what the data type is. So I'm recommending you store the data type in an array of length n-1, because the tree requires n-1 non-leaf nodes. Okay, so how do we do this? Here are my transactions. A gives B1, B gives C2, A gives G4, whatever. I had to make some stuff up, right? Suppose these are your transactions, right? You can store these in an array or a list here, whatever. This is sort of looking like it's a matrix representation. That's kind of confusing, but that's okay. So in a complete binary tree, the last row is a power of 2 in size. But we don't actually have to worry about that, right? Because we can just start filling out a last row until we get enough stuff we want. And I'm going to show an example of that. We have 6 entries, so we're going to need part of a row of size 8, which is probably row 3, depending on how you count it, and part of a row of size 4. So how do we do that? Well, I go ahead and I start with my row of size 4. And this isn't big enough to hold all of my transactions, right? This would only hold A, B, C, and F, right? Which are the 4 grades that you can... No, there's no D. Okay. Okay, so I can just start slamming leaves on here, right? And so the first thing I do is I pick the leftmost child, and I give it 2 children of its own, right? And then we have 1, 2, 3, 4, 5 leaves. Still not enough. That only gets me to G. And I got another A waiting here. Not to worry. I just give this thing 2 children. Boom! Look at that. 1, 2, 3, 4, 5, 6 leaves. Easy peasy. Ez pez, as they say. And you can do this mathematically and algebraically, but I just wanted to show you an example. Also, doesn't this kind of look nice? I think that there's like some aesthetics going on there. Okay. This is how I imagine plugging these things all in together, right? So I have my tree, I have my maximal root. It has a left and right child. Its left child has left and right children that have leaves. Its right child has children that do not have leaves, that are leaves, right? So it gets a little wonky, right? But anyways, we have these 6 outermost elements in a row, and each one of these 6 elements points to one of the transactions, right? This makes perfect sense. We can all agree this makes perfect sense? Okay, so I'm going to relate the transactions to leaves. And I've switched to just spelling leaves normally, because I don't want you to cook me in the comment section, okay? Then we hash. How do we hash? Well, each one of these leaves contains the hash of the transaction, which I stylize here as just a hash with 3 arguments, the public key, private key, and the amount. That's not exactly what we agreed we were doing before, but I just needed some way to relate this linguistically, right? So we put our hash values in each of our leaves, right? Easy peasy, nothing too complicated, right? Now what am I going to do? Now I'm going to hash these hashes and put it in that node, right? I'm going to hash these hashes and put it in that node, and hash these hashes and put it in that node. So, these become the hashes of the transactions. The next layer up becomes the hashes of hashes, right? So I hash, and that says star 0xa and 0xb, which I take to denote, oh, I flipped these, which is okay. So I take that to be the value at that location, right? And star 0x7, or 0x6 and 0x7. And I only numbered this in hexadecimal because I needed to get up to A and B, okay? It was not very easy to change the alignment.
I mean, I think.
Yeah. You can look at the source code. It's not that bad. Have you seen this? So this is called hashes. Right, so I actually only specify nodes and edges. And then I also specify a rank direction. And I think to get it to look the way probably we both want it to look, I have to create subgraphs and connect them. And it's a lot of overhead. So that's why I didn't do it. But, I don't know, you're an enterprising young student. You can take a look at this and try and fix this. And see what you think. Well, so I would probably suggest all of you spend like 5 minutes at some point in your life figuring out how graph viz diagrams work, because I learned them for a different class and now I use them for everything. Like, these things just work. I used them for... Hold on. Okay, one more aside. Is it not on here? Okay. Sorry. Research. Where is it? Okay. Right. So these things, you might have to make something like this in your life, and it's just like you want to have a framework to make it. I made this in draw.io because I'm lazy and not very smart, but it should have been made in GraphViz, and I feel bad about it. See? Okay. So anyways, you will need to make things like this, and GraphViz is a good way to make them. Okay. All right, I'm extending the metaphor. This is the Merkle tree. This is the Merkle root. Okay? The Merkle root, I don't know, seals or signs or provides integrity to each transaction through this sort of nested tree structure. I take that Merkle root and I put it inside my Bitcoin. You can either hash it or not hash it. I guess I don't know what they do by convention. Let's see, that is... Yeah, that just contains the hash. So that should probably just say hash of 2,3, right? So I have the hash of the previous value, I have the timestamp, I have the nonce, then I have the hash of the root, right? This is a Bitcoin block. The Bitcoin block implicitly includes these transactions, right? And if I change let's see, how would I change this to steal money? If I change A to Kelvin, it breaks this hash, which breaks this hash, which breaks this hash, which breaks this hash, which breaks this block, right? So nothing can be tampered with without... You have to tamper with this in some way that you get the same hashes all the way up, right? And that's Merkle trees. Last two things I'll show you. I kind of wanted to show what this looked like to me when I'm thinking about how I would put this in program, or not program, in system memory. So I have over here, I have Bitcoin blocks. They have a hash of prev, a hash of a root. That's the root of the Merkle tree, right? They have a time and a nonce. The hash of this thing goes into the hash of previous of another block, but the hash of the root comes from what hash? It comes from the one index of a linear data structure, right? So this is the linearization of that tree I showed you earlier, right? This linearization, the second half of its linearization is the hashes of transactions, and the first half is the hashes of transactions, okay? So each one of these hashes in the second half of the linear data structure corresponds to a transaction. And this transaction itself is a linear data structure. What I would like you to see looking at all of this is I have like a lot of graph theory going on here, and I can put all of it in an array. And as soon as I put it in an array, I can type fwrite inside my C code and just write it to a file, right? And I have to know it's written to the file, so this is relatively sloppy file I/O, right? But you can do it, right? You can just write it directly to file, okay? And then here is an example of how I would declare these data structures, probably, or one way to do this. We introduced ints earlier, but I also sort of wanted just a hash type. I don't know. It's kind of weird to me to pass around 256 bits in any way. I just kind of feel uncomfortable with them no matter how I do that. You've previously seen the transaction structure, right? Where we have the sender modulus, which is its public key, the receiver modulus, which is its public key. We have to have both public keys because someone has to sign it to start the transaction, and then someone has to sign it to transact it to someone else, right? So we need both public keys. Then we have an amount. Here's my signed transaction struct, which I solved with chunks, right? And then here is my hash t struct. I didn't overthink this at all. I counted how many transactions I have. I had a Merkle tree of hashes, which is the linear data structure of hashes. It's this thing, right? And then I have a linear data structure of transaction trees. That's right here. And each of these transactions is one of these things, okay? I think it's new to write a type def and a struct definition in the same line. I have historically considered it poor form, but I was trying to save space on this slide, and it basically works. It is somewhat logically different in a way that is extremely, extremely out of scope for us. Okay, with that, I just want to take a few minutes to go over heap t. Okay. Wait, no, okay, announcement. No in-person class on Tuesday. Zoom Tuesday. I'll send an email. I was not going to send an email before this class because I was worried you would be confused which class was on Zoom. So sometime tomorrow I'll send out the Zoom announcement. It will be from 3 to 4. It will be on Zoom. We are meeting a guest speaker from Galois who's going to talk about something. You're expected to politely ask questions and hopefully get a job. Okay? All right. Heap t. The due date for this is the last day of class because I am not allowed to set due dates during finals, and I don't know when that is. But I would usually give you a little more time for this, so you should just take a little more time, turn it in late with no late penalty if you want. So this is the exception to start working on the next thing when this is done. If you haven't finished this, here's how I am thinking of this class. This is the final. How do I describe the final? You should do this if you are interested in research, engineering, or computer science and not busy, and then you should finish this final by May 9th. If you are not in one of those populations, or if this is your first 200 level class, this is an optional final for undergraduates. I'm just providing it for everyone. I had to develop the final for the MSCS students anyways, so I'm giving it to you to let you do it. These are some interesting things, and they can produce publishable results, especially if you want to work with me a little more. But you don't need to feel a need to do them, right? So you should probably be in conversation with me about that if you want to do that. Okay. The actual final, and I think you should all want to do this, the actual final for undergraduate level is heap T. Because as soon as you implement heap T, you have implemented all of the required components to implement blockchain. And it's really just an integration task. And I don't necessarily think of the integration task as particularly interesting, right? So the way I made it interesting here is I was like, oh, like throw it all under version control and have it run automatically. And like, that's kind of cool, right? But it's not theoretically interesting. So this is the final. I've given you a tester and I've given you a header file. I didn't give you a .c file. I assumed you could make your own. Right, this is essentially a data structures assignment, so it's going to feel very similar to presumably other data structures assignments you have. There's an initializer or a constructor. Heaps need to know the size of their elements and also their greater than. This is your first mandatory function pointer. I understand that as an escalation in difficulty. That's why it's here. This heap should hold the way it sorts its elements. The way it sorts its elements should not be placed anywhere other than inside of the heap. That is where it's used. That's where it should be maintained, right? The heap struct, and you are not required to use all of these, but you should use at least the void star. Mine contained the size of its elements, the number of elements it contains, and its maximum capacity. My internal array, I just doubled it in size every time I ran out of space, which meant I often had more capacity than elements. This is like cool in some way. You don't have to do that, but if you do that, you have to maintain capacity separately. But you minimally have to count how big your elements are and how many of them you have. I've asked you to store your greater than function inside of the heap structure, and I also want you to have an array of void stars. They have to be void stars because we don't know how big they are, right? Okay. Here's the explanation. Okay, so that's your initializer constructor. Insert is the next interesting thing, and I didn't over-describe it because I feel like I just showed you how to do heapify and heap insertion quite clearly in class, okay? Popping the maximal element is non-trivial because it includes sift down, which is kind of the negation of heapify, but it is more complicated. Why is that? When we pop the maximum element at the heap, in order to maintain a perfect tree, we have to take the rightmost leaf in the last layer. And we have to move that to be the new root, because we have to get rid of the element at that position. So we take that element and we move it to the root. That element is necessarily smaller than one of the two nodes, which means the heap property of the maximum being in the root is no longer fulfilled. So you have to perform a sift down. Here's how sift down works. You take the leaf, so I pop 224 and I take 128, put 128 in the root position. We notice that 128 is not the maximum, so we find the maximum of its children and we swap it with the maximum of its children. Okay, the maximum of its children is 92, we swap it with 92. You do that until you run out of children, then your heap property is still preserved, everything is greater than both of its children, right? This is how we maintain generational wealth inequality. Yay! Okay. I've provided you a tester that is very much similar to the list T tester. It just prints out the heap at a bunch of different times, and I have to do some mucking about with pointers to get that to work gracefully, but I got it to work. And then here is the heap T, and of course, you can just open these somewhere else if you'd like them as well. So that is the final assignment, and I think it's going to be cool and fun, and if it's not, we'll do something different next year. Thank you. Any questions? Really, there's no questions. You're not going to ask, how is this so much fun? It's when it's why are we what? So if we do this on Merkle trees, oh, do you mean instead of trees in general, like n-ary trees? Yeah. If you want to implement either a Merkle tree or a binary search tree, you should do that as your final. And if you want to do it instead of heap T, I won't stop you. What kind of tree do you want to do? Why don't you implement a strict Fibonacci heap? Like, that sounds cool. Have you done one?
I've never done it. You think that being not that great. Maybe the strictly fix it.
No.
Probably not.
No, so the way they got better worst case time bounds on everything is they just added a ton of constant time costs. So they do like massive data duplication and everything. But then I'm thinking like, isn't this just a data lake house, right? Isn't that what they do? So I think we should implement one and release it as a Python library. And I think we should get credit for 2 languages by writing a Rust implementation of a strict Fibonacci heap and then implementing that as a Python library, right? So you're like, I am a Python Rust developer. That's what I want to be. Yeah, so that's why everyone loves polars. There is no class on Tuesday.
Or there's Zoom.
There's class on Tuesday, but it's on Zoom. Uh-oh. Oh no, okay, I'm leaving. Yeah, I think we're over. Is class over? Cool. I won't see you on Tuesday unless it's on Zoom.
Tuesday, and then bring the
No!